Hi, welcome to join us for this camera driver development and porting hands-on video. I will go through the source code and give instructions to help you develop your own camera driver on JSON platform. Before we start, please download L40 source packages from the JSON Download Center. This video is to demonstrate sensor driver porting based on Sony IMX185 driver. The sensor driver is under kernel folder. In general, we separate sensor driver code and sensor mode table into two source files. The sensor device tree is under the hardware folder. JSON Camera Serial Interface (CSI) is based on the MIPI Alliance specification for Camera Serial Interface 2. Sensor is connected to JSON via CSI. The CSI block works as a receiver of the bare sensor MIPI signaling and a source of pixel data to the video input units. CSI block is used to deliver not only bare but also YUV, RGB AAA, and etc. The VI block, which receives data from the CSI block and can route data to either the ISP or directly to system memory. VI kernel driver for TS1 is based on VI hardware block version 2, whereas TS2 is version 4. For more details on CSI and VI, please refer to Technical Reference Manual. Let's describe device tree porting first. All imager devices have one media path for binding the connections. That is from sensor to CSI and then VI. For the sensor to CSI port binding, CSI port indicates CSI port number 0. When you have second camera, the number will be 1. Bus width is to identify the number of CSI lanes connected to each sensor. For the CSI to VI binding, number of channels defines number of camera sensor unconnected. You will need to update the value and extend port definitions if you have more than one camera sensor connected. Bus width is to identify the number of CSI lanes connected to each sensor. Remote endpoints define the label for binding two ports. The binding is passed one port as an output and the other one as an input. This module information is to describe each sensor identity. When porting to the different sensor, you should also modify the device name with respect to its device name and I2C address. The port device tree property represents the path of the camera sensor device node. If your system has multiple modules that are identical, create a unique batch name for each module. For example, if you have one module for a rear-facing camera and an identical module for a front-facing camera, you can call the rear camera module IMX185_rear and the front camera module IMX185_front. Each camera sensor supports several camera sensor modes. For instance, IMX185 supports 1080p, 720p, etc. The properties for each mode is also stored inside the device tree file. These properties specify the mode information for each different sensor mode. Please also check the sensor spec to fill in correct values. Camera driver programming guide covers the details of each property description. I would like to emphasize below two properties. CIL setup time, specify the value of the THS setup time of the MIPI LAN. A 0 value means auto-calibrate. Embedded metadata high. Specify how many extra embedded metadata rows for each frame. Set to 0 to disable embedded metadata support. Please notice that CMOS sensors need to follow the rolling shutter rules. Exposure time needs to be less than or equal to frame length. Frame length needs to be greater than or equal to real time. Also, we don't support global shutter at this point yet. Pixel clock, exposure time, or frame rate is calculated based on sensor spec. As you can see the kernel sensor driver code directory, this allows you to build 3 different drivers: sensor driver, CSI driver, and the VI driver. However, CSI and VI drivers remains unchanged when adapting to different sensors. 4 key functions for sensor driver portings are sensor probing, power on off sequencing, start sensor streaming, and V4L2 control CIDs. Out of these 4 functions, sensor probing is only run once during kernel initialization stage of system boot up. For a typical camera application running cycle, the driver will power on the sensor, start sensor streaming, sending relevant V4L2 controls, and finally, power off the sensor. Sensor probing function is the very first function get called during kernel initialization stage. It includes device tree passing function to obtain M clock and GPIO pin settings. The parse function will also check device tree ID according to its driver name. The driver name inside sensor driver should match the one in the device tree. Here's power on off function to indicate the sequence of the power supplies. Please also check the sensor spec to confirm the correct power on and power off sequence. Prior to sensor streaming, sensor driver will establish proper sensor mode based on the application request. If the requested resolution is not exist in the mode table, it will choose the costless resolution. The driver will use default exposure time to program the frame and start the streaming operation. V4L2 CIDs allows application to control the sensor settings. Here is the camera common structures that contain standard V4L2 CID controls. Here's CID to specify the supported color formats, and CSI ports for driver mappings. For gain, frame rate, exposure time controls, you should refer to the sensor spec. JSON platform included an double EEPROM that enable the dynamic selections of the different sensor modules. If your camera module board do not have double EEPROM, here is how to disable the plugin manager to avoid detection failure. Congratulations, up to this point, your driver porting is complete. Now your driver porting is complete. You will need to compile the sensor driver and the sensor device tree. Once you rebuild the kernel, your binaries will be included in the image. For your binary to take effect, simply refresh the DTP partition and replace the kernel image. When system reboot, your sensor driver should be loaded and run. Some of the tracks can be observed for your new drivers are plugin manager active in the very first kernel init state, probing function to detect the camera sensor, register the device node under /dev/video0, etc. To verify your driver implementation, you can use standard Linux v4l2 compliance and v4l2 control to ensure their v4l2 compatibility. The v4l2 compliance tool is used to test video for Linux devices. Please note that v4l2 compliance not only tests for compliance against the v4l2 API, but also whether the driver is using all correct frameworks. The v4l2 control is another tool to test video for Linux devices. You can assign output resolutions to testing your sensor driver. Also, here is -string -2 parameter allow you to dump the sensor streaming into a raw file for further analysis.